Hi! So, usually I'm known here on YouTube more for my AP US history videos. Well, I keep getting a lot of comments saying, are you going to make more of the history videos? Sorry, I'm not in AP US anymore, so I cannot make any more of those videos because I don't have my stuff anymore from that class. And I don't really remember all that much of it, to be honest, anymore. But I make these videos to help me study for tests and hopefully help someone else at the time. So, that does not mean I won't make any more educational videos. In fact, this is an educational video, but it is much different. I'm in forensic science, and so I'm going to be making a couple forensic science videos. This one is about arson, and the next one is about firearms. So, if you want to learn about arson and forensic science, watch this video. Again, it helps me study, and I'm not an expert on this by any means. I've read my notes, and I'm just going to go through the slides. You won't see them, but I'll see them. But I'm going to try to go through the slides and articulate the concepts as best as I can. So, arson crimes are pretty difficult to solve. Only 17% of cases in 2003, 17% of arson cases in 2003 ended in arrests. Vandalism is the leading cause of arson. I was thinking about that. I'm like, why is vandalism? Like, fire should be the leading cause of arson. But anyway, I think that, like vandalism, people vandalize stuff, it tends to cause the most arson. Also, an estimated 25% of arson fires are drug-related. So, lots of people who start fires are drugged up. At least a fourth of them. So, let's just talk about fire itself. Fire is the result of an oxidation reaction. And oxidation is a chemical reaction between a substance and oxygen. Oxidation, oxygen, makes sense. Now, the speed of the oxidation affects how the whatever's being burned is going to be affected. Slow oxidation will only create like rusting or bleaching or such. Now, when you have fast oxidation, you have more of a rapid release of heat, and you're going to have combustion or fire. Now, when you have really fast oxidation, this is when you have explosions. So the faster the oxidation, the more dangerous, fiery, flammable the reaction is. Now, chemical reactions. What makes them happen? Well, we have spontaneous reactions, which are what cause fire. Basically, the driving force for any system is they always want to move to a lower energy state. My teacher was like, it's like teenagers. What do teenagers always want to do? The least work possible to get stuff done. So, think of the spontaneous reactions as lazy teenagers. You always want a lower energy state. And potential energy is stored in the chemical bonds that are holding these atoms together. And when a spontaneous chemical reaction or spontaneous chemical change happens, this energy that was stored between the bonds is going to be released. And it's going to produce heat. Exothermic reaction is when heat is produced. An endothermic reaction is when heat is absorbed. And that makes sense. Exo meaning out, endo meaning in. Now, how does reaction start? Reactant particles must make contact or collide with one another. So the collisions must have sufficient energy to break the bonds that hold the atoms together. So we have these particles. They're colliding with one another, but they have to have enough energy that it starts breaking bonds and something happens. Activation energy is the minimum amount of energy that reactant molecules must possess to react. So you have to have enough activation energy. That's the minimum amount for a reaction to take place. Factors that influence the intensity of a fire. The intensity of the fire increases as the rate of the chemical reaction increases. That makes sense. So the faster the reaction, the more intense the fire. There are 3 ways to increase or decrease the rate of a chemical reaction. 1. Manipulate the temperature. 2. Change the concentration of reactants. Or 3. Add a catalyst. All of these things will increase or decrease the rate of a chemical reaction. But with arson, we really focus on temperature, the state of the fuel, the concentration of the reactants, and the use of accelerants. So this is like things we want to focus on in the forensic analysis of arson. So there are the factors that influence the intensity of a fire. Let's focus on that temperature. Fuel will only produce a flame only when sufficient molecules exist in a gaseous state. So fuel just doesn't produce a flame. You have to have the right number of molecules to produce that reaction. And the temperature must be high enough to vaporize liquid fuels. So it's got to be hot, and it's got to have the right amount of molecules. Not too much, not too little. Flash point is the minimum temperature at which a liquid fuel will produce enough vapor to burn. So a liquid fuel must reach its flash point for fire to be produced. Flammable liquids have a flash point of less than 100 degrees Fahrenheit, while combustible liquids have a flash point of equal or over 100 degrees Fahrenheit. And once a liquid reaches its flash point, fuel can be ignited by an outside source of heat. So once the fuel gets to that heat, to that temperature, then it can go. And the ignition temperature is higher than the flash point. To be honest, I'm not quite sure what that means, but I think it might maybe like whatever ignites it must have a temperature higher than that of the flash point. Or after it ignites, it's hotter. I'm not quite sure what it means. So factors influence the intensity. Accelerants. Accelerants change how fast something like the fire goes. Here's the definition. Materials used to start or sustain a fire. So the accelerants kind of make the fire happen. Liquid accelerants form flammable or explosive vapors at room temperature. And what are plastic materials to burn when heated to a temperature that is hot enough to decompose the solid and produce combustible gaseous products. So basically liquid accelerants don't have to, they can be room temperature to create a fire. But wood or plastic, like, with the fires and stuff, you gotta get it hot enough to catch on fire. You can't just be like, wood, commence fire. It does not work that way. It has to be hot enough that the actual fire reaction is occurring. The effects of concentration also affects the intensity of a fire. If the ratio of gaseous fuel to air is too low or too high, the mixture will not burn. So you need to have, you can't have too much air, you can't have too much gas, you have to have the right amount of both. The flammable range is the concentration of gaseous fuel that will support combustion. So you're in your flammable range if you have enough fuel. The lower explosive limit is the lowest concentration that will burn. Just think of, if you're in calculus, think it's like the lower and the upper limit. So the lower explosive limit is the lowest concentration that will burn. So that's the least amount of gaseous fuel that will burn. And the upper explosive limit is the highest concentration that will burn. So you have your lower and your upper limit. And that creates your flammable range. Apologize, I'm shaking the screen a lot. Laptop's on my lap. The rate of chemical reactions increases as the temperature rises. That makes sense. Hotter, faster reaction, more fire. As the fire burns, it raises the temperature of the fuel-air mixture, which increases the rate of reaction. Makes sense. The fire produces heat. It is being exothermic, and thus the temperature rises. In most structural fires, oxygen from air is a necessary reactant to keep the fire burning. Oxygen is a necessity for fire. That is why there's fire blankets and such, because you're smothering the oxygen from the fire. You're starving that fire, and that's why it goes out. And now, there's different stages in a fire. The first stage is the incipient stage. I think that's how I pronounce it. INCIPIENT. Incipient. I think incipient stage. Sorry, my phone. The stage, it begins with the ignition of the fire. So that's the very first, the start of the fire. The gases start to rise in the room. The oxygen goes to the bottom, and the oxygen starts feeding the fire. So it produces a V pattern on vertical surfaces. So when it burns, there's that's all filled in. There's a burn mark on the wall like that. There's a picture on my screen, but unfortunately I cannot show you said picture. Can't show you my screen. The sequence of events. The next stage is the free burning stage, where the fire consuming more and more fuel, and it's intensifying, and the flames are now spreading upward and outward, and the fire's everywhere, and there's a dense layer of smoke and fire gases that start accumulating near the ceiling, and at a temperature of 1,100 Fahrenheit, all fuels in the room ignite. That is your flashover. So that's boom, that's when the fire's getting out of hand. And if the fire stays confined to the area it originated, its growth depends on the amount of oxygen available. So, if it's contained, it has to keep having oxygen or it's going to go out. The entire structure is now engulfed in flames. It makes sense. This is the free burning stage. There's lots of burning. Logical. Next stage is the smoldering stage. This is when all the fuel is consumed and the fire's open flames disappear. So it's used up everything it can to keep making the fire. It's dying down. Now, if oxygen comes into the area, the soot and fire gases that are left over from the flames, they can ignite with an explosive force. So they can all go boom, and it produces what is called a backdraft. And the pressure generated by a backdraft can cause significant structural damage and endanger the lives of firefighters, because if firefighters put the fire out, they're going in the house, but maybe some oxygen goes in and causes some explosions that would I can't talk. That would stop phone. I'm going to silence my phone for you guys. That could really hurt firefighters. Now, let's go into accelerants. Hydrocarbon accelerants. Hydrocarbons are composed of two elements. Can you guess what they are? I bet you can. Carbon and hydrogen create hydrocarbons. Wow! And we have, I don't know how to pronounce this, alkanes. And we have, these are like methane, ethane, propane, butane. All of these things make fire go boom. As the carbon chains in an alkane grow longer, the properties of the members change with increasing molecular weight. I don't know what that means, to be honest. But there you go. There's the words. You can interpret it as you want to. Structural isomers are compounds that have the same molecular formula but different structures. So, formula is the same, but they're made differently. Kind of like today. Metaphor. Today in calculus, I got the answer correctly right. Like, exactly right. To the decimal, everything. But I went about the whole problem completely inaccurately, so I don't know how I got the answer. So it was structured a different way, but the end answer was the same. Petroleum is a hydrocarbon accelerant. It is the main source of most organic compounds used by industry. Crude petroleum is sent to a refinery and separated into fractions, which is called fractional distillation. And each of these fractions contains a different mix of hydrocarbons. So if there's a fire and there's debris left over, and they can analyze the hydrocarbons in it and figure out like what kind of accelerant was used, because when the petroleum split, the hydrocarbon amounts in each fraction are different. Okay. We want to find the origin of the fire. I'm not going to go into the geometry because we don't have to know that. But the point of origin is where the fire started. Makes sense. Typically, the site of greatest damage. Again, makes sense. It was burning the longest. When investigators go examine an arson, they often work from the exterior to the interior and from the areas of least damage to greatest damage. And this method of searching is called the backwards theory. There's a picture. Okay, burn patterns are the physical marks and char that remain after a fire. Makes sense. Lines or darkened areas record the boundaries between different levels of heat and smoke. Makes sense. That, you know, the marks that the fire created will help you know maybe how hot it was or where the fire was. The direction the fire traveled can be determined from burn holes in walls or ceilings. Remains of damaged material may provide clues about the source of the fire. And measuring the depth and extent of charring may help estimate the duration of the fire. So, basically, examining all that debris, you can figure out, you know, how the fire, how long it had been, you know, burning, where it is. Oh, I'm really tired. Obviously, though, like, where there's the most damage, that's where it, started. And there's a picture, and I'll try to kind of summarize it for you because it is helpful. There is a piece of wood like this, and here is where the fire was. There's some char. This is the depth of the char. Like, here's this much is wood, that much char, that's the depth. So there. That's the depth when they're talking about looking at the depth of the char. How much it burnt into the wood. Burn pattern geometry. Again, the shapes on the walls or floor may indicate handling of accelerants. A V pattern means that the accelerants came from a container. So if there was like a bucket of the accelerant, that's going to create a V pattern on the wall. Now an hourglass pattern on the wall means that there was a pool of burning liquid. And there was a picture in the notes that showed, like, here's the wall, here's the floor. There's like a pool right here, and then on the wall is the hourglass. A pour pattern is just a burn in the middle of the room. It looks like a puddle just in the middle of the room. That's where the accelerant was. A trailer pattern is a burn pattern that resembles a flowing stream. So that means the liquid was spread from one location to another. And that kind of looks like, as an example, there was a door, and there was a flow, like a burn mark that kind of looks like a little river going from it. And that would be a trailer pattern. Again, I wish I could show you the pictures. Melting of materials. The investigators can estimate temperatures of the fire by examining the melted objects. Melted objects assist in determining the intensity and duration of the heating, the extent of heat movement, and the relative rate of heat release from fuels. So if we can look at the melted objects, we know how long it was hot. The extent of the heat movement is not quite sure what that means, but basically know how long it was hot, how severely it was hot, and how fast the heat was being released from the accelerant. Also, discolored metals can show us things. Discoloration indicates that the fire was extremely hot, and metals retain their discoloration even after the fire ends and they cool down. So forensic scientists can still go in, still find which metals are discolored. Indicators of arson. Charring of floor surfaces. It does make a lot of sense that charring would be an indicator of arson. Area of burn floor adjacent to unburned floor is a reliable sign of a liquid accelerant. So, if there's like burn floor, unburned floor, that might be a liquid accelerant. And accelerant can often be detected in the corners of a room or along the base of a wall. Containers can be evidence. Liquid containers are evidence. If it is not damaged, they may be able to retrieve fingerprints left by the arsonist. So if the accelerant was in a container, they can check for fingerprints, see if they can find the arsonist. They may indicate use of a liquid accelerant. It should make sense. You would use that, even if melted. Odors from the liquid accelerants also can help you. Many of these odors evaporate quickly, so you have to get them as fast as you can. Contaminated areas from the fire can be detected with ultraviolet light, I think that's a typo, or a hydrocarbon detector, or specially trained dogs can detect the accelerant residue. So you just need to find the accelerants as fast as you can, and I'll go a little more into that in a minute. Now, to collect and preserve your evidence, at the scene you need to search for, identify, record, and photograph all evidence and notice location in a sketch. That was the first unit we did in forensics. It is important to document everything you find. Photograph and document the conditions of doors, windows, and locks. Could provide for good evidence. And look for accelerant residues at the edges of burn patterns. Collect debris suspected of containing accelerants and place it in clean metal paint cans. It is important that you use metal paint cans. Don't use plastic, because if you use plastic, it'll absorb the compounds and it's going to ruin the sample. And the paint cans help because they're airtight, because you need to keep the vapors in there. You don't want them to escape or be tainted. And in the laboratory, open evidence storage units as briefly and infrequently as possible to minimize escape of vapors. So if you're looking at what's inside the can, don't spend a lot of time doing that. Close it as fast as you can. And the nature of the debris may dictate that the examiner carry out a certain type of test. So, what kind of debris is left tells you what kind of test you need to do. One test is heated headspace sampling. This is when the examiner, they put a piece of fire debris in a special metal container, kind of like the paint can, and you heat that container. Then you take a syringe and you puncture the rubber septum. Syringe is used to puncture the rubber septum, so I'm guessing there was rubber over the top of the thing. And you use the syringe and you suck up a bit of that vapor, and you eject it into a gas chromatograph to sample, but the little downside of that is only a small portion can be sampled. Another test is solid phase microextraction. Oh, I skipped too many. Sorry. Next is passive headspace diffusion. You have this little carbon fiber mat that is suspended in a container with the debris. So again, you have another container, something in it, the debris in it. You heat the container once again, and it turns the liquid accelerant into a vapor. Then you take a charcoal or a carbon strip, which absorbs the vapor, and it concentrates it. And you can extract the accelerant from the carbon strip, so then you can figure out what accelerant it was. Now we have solid phase microextraction. This, instead of the carbon fiber mat, you replace that with a solid phase absorbent bonded to the fiber. Again, some of this stuff, I don't know what it means. But there you go, make of it what you will. You insert this material into a container of fire debris with a hollow needle. So the fire debris is already in the container, and you put the absorbent with the needle into the container. The container is heated, and the absorbent material is withdrawn from the can and inserted into a gas chromatograph. So again, using the gas chromatograph. And now we go into that. Gas chromatography. It's used to separate and detect complex mixtures of volatile organic compounds. And it's going to distribute the compounds of the mixture between an inert gas mobile phase and a solid stationary phase. And through all this fancy science mumbo jumbo, it's basically going to take the components that were in it and separate them into peaks. So the area under each peak is proportional to the concentration of that component. So now you know what is in that accelerant. Some arsonists use a mixture of accelerants though, so this poses problems. So to overcome this, a GC may be attached to a mass spectrometer, which indicates which components are contained in each accelerant. So that helps narrow it down. Those are all the arson notes, and I will be making a video about firearms later, so bye.